In lab number 12, we're introduced to multicast routing. We begin by reviewing basic multicast theory, and we'll see the syntax to set up multicast. Then we'll go out to our routers and we'll set up globally on those routers IP multicast. We also have some configuration work to do down at the interface level. We'll verify that basic configuration, and we'll even set up a router to join a multicast group. And when it joins that multicast group, we're going to be operating in PIM dense mode. We will verify that operation, but for the real world, we probably would prefer to run in PIM sparse mode. So the next thing we'll do is to set up a rendezvous point. And then we will be running in PIM sparse mode operation, and we'll verify that operation.
In this lab, we want to consider multicast. And to understand the benefit of multicast, let's think of a scenario. Let's imagine that we have a video source, and we want to send this video stream from the video source out to 5 recipients somewhere on the network. And let's say that we have 20 computers on the network. If we were to use unicast, the source would send a separate stream of packets to each of those 5 receivers. That's one way of getting this stream to multiple recipients. But I suppose a downside is that this solution would not scale very well if we had to send to many other recipients and we're consuming extra bandwidth on that video source link. Another way to send out this stream of traffic from the video source to the 5 recipients would be to use broadcast. If all of these recipients were members of the same subnet or the same VLAN that the video source was participating in, we could send out a broadcast, and this would make sure that everyone in the entire subnet got this video stream, and the source only had to send the stream one time. But the downside of that is everyone received the stream. In addition to the 5 recipients that wanted to receive the stream, it also went to 15 recipients that did not want to receive the stream. But the best of both worlds is multicast. With multicast, a source can send a single stream of packets, and that single stream is replicated as needed amongst the routers and the switches in the network, and it only goes to those receivers that want to receive the traffic. How does this work? A multicast source, the video server in our case, is going to send its single stream of packets out to a Class D IP address. This Class D IP address is known as a multicast group. You might remember in your early studies of IP addressing that a Class D address would have a number in the range of 224 through 239 in the first octet of the IP address. As an example, let's say that we have a multicast group of 224.1.1.1, and as we see on screen, we have 3 PCs that are members of a particular VLAN, but only 2 of those PCs, only 10.1.1.1 and 10.1.1.2, only those 2 PCs want to receive traffic from the multicast server. And notice the multicast server is sending traffic destined for that Class D IP address, 224.1.1.1. We have a non-receiver of 10.1.1.3. With multicast correctly implemented, the switches and or the routers in the network will send traffic only to those devices, only to those receivers that want to receive the traffic, giving us again the best of the unicast world and the broadcast world. And in this example, I used a multicast group of 224.1.1.1, but in the real world, inside a corporate environment, it's common practice to use 239 in that first octet. The reason is 239 in the first octet, that represents the private range of IP multicast addresses. This is similar to the 10 dot address space that we have for a Class A network. You might use the 10 dot address space inside of your network but not route it outside of your network. It's private IP address space. It's very similar for the 239 address space. That's the private IP address range for Class D addresses. Let's now continue with our discussion of basic multicast theory by understanding how a receiver joins a multicast group. The receiver is going to join a multicast group by sending out an IGMP join message. IGMP, that's the Internet Group Management Protocol. And when a receiver's IGMP join message goes into a router, that router knows that if it receives traffic for the specified multicast IP address, for the specified Class D address, it knows that if it receives traffic for that address, that it needs to forward traffic out of the interface on which it just received the IGMP join. In the example on screen, we have a receiver that sent an IGMP join message up to Fast Ethernet 0/0, and this IGMP join message would contain a Class D IP address. So when this router received traffic destined for that Class D IP address, it would know that it should forward traffic out of Fast Ethernet 0/0. And IGMP, that's one of the multicast protocols we see quite a bit. And that's used between our routers and the multicast receivers. But another protocol that we might have that runs between routers is PIM. Multicast routers can route multicast traffic using Protocol Independent Multicast, or PIM. Protocol independent meaning that we can route multicast traffic regardless of the underlying Layer 3 routing protocol. We could be using OSPF or EIGRP. That underlying routing protocol does not impact the operation of PIM. And when we talk about PIM, realize that PIM has two modes of operation. There is PIM dense mode and PIM sparse mode. First, PIM dense mode is going to use a flood and prune behavior to build a multicast distribution tree. Let's talk about what that means. We mentioned that when a multicast source sends traffic throughout a multicast network, that traffic would be replicated appropriately by routers and switches. The replication of that multicast stream can be visualized as branching out to all the receivers to form a tree, a multicast distribution tree. And with PIM dense mode just assumes that everybody in the topology wants to receive this traffic. So it floods the multicast traffic throughout the topology to all the multicast routers in the topology. But many of those multicast routers might not be attached to receivers for that multicast group. In other words, those routers would have no need to receive this multicast traffic, so they do not need to be a part of this multicast distribution tree. What those multicast routers can then do is send a prune message to say that they no longer wish to participate in this tree. The bad news is this flooding and pruning behavior by default repeats itself every 3 minutes, which can cause quite a bit of traffic on large multicast networks. So typically we're not big fans of PIM dense mode. We much prefer PIM sparse mode. With PIM sparse mode, we have a common point in the network that all of our receivers can come to if they want to receive traffic for a particular multicast group. This avoids the flooding and pruning behavior. This rendezvous point, or this RP, is going to receive traffic from the multicast source, and then we've got our receivers that come up and join this tree by pointing to the rendezvous point. However, that could lead to some suboptimal pathing, so fortunately traffic does not continually flow through the rendezvous point. We're going to go through a shortest path tree switchover, or an SPT switchover, which allows us to build an optimal path between the receiving router and the router attached to the multicast source. I think we can make more sense of that by actually seeing that in a topology. Here's the topology we've been working with throughout all of our labs. And what we're going to do in this lab is first illustrate the operation of PIM dense mode. With PIM dense mode operation, we're going to have router R2 acting as a multicast client, and I will show you the command that will allow a router interface to join a multicast group, much like a PC might join a multicast group. And the specific group we're going to be working with is 239.1.1.1. We're going to have router BB1 acting as a multicast